Hi, my name is Jaimen Angelino Allende and I attend Coral Gables Senior High School, and we will be discussing how the atom became and the history behind it, the subatomic particles in atoms, isotopes and ions, average atomic mass and isotope percent abundance, and finally real-world applications of atomic structure. All of these topics will be covered, and by the end of this short segment, all of these topics are going to be easy to comprehend, no doubt. We will cover some easy math calculations and have visual examples. Now, before we begin, let's take out our paper and pencil. These days, most people are aware of what an atom is, and they accept that they make up things around us, which is pretty right so far. But for a long time, atomic theory was controversial, and to understand chemistry is to understand the process by which these particles and their components came to be accepted knowledge. Let's see. Democritus, a Greek philosopher in 460-370 BCE, was the first to propose that matter is comprised of fundamental indivisible particles, which he called atomos. Though this marks the first time matter was viewed in this way, it was more of a philosophy than a real science, and no supporting evidence was gathered for a long time until John Dalton came along and provided the first empirical evidence that atoms exist. He proposed that compounds consist of different types of atoms in whole number ratios, and that chemical reactions involve the rearrangement of the new given combinations. His idea explained that certain observations, for example, when a sample of water was split into hydrogen and oxygen, the result was always 1/9 hydrogen and 8/9 oxygen by mass. Which atomic theory, this makes perfect sense if we understand that water is made up of tiny water molecules and that all have the same exact number of hydrogen and oxygen atoms. Then no matter how much water there is, it will always have the same ratio of hydrogen to oxygen by number of atoms and therefore also by mass. It also explained the way certain elements combine to form different compounds. If carbon reacts completely with either a certain mass of oxygen and precisely double the mass of oxygen, that probably means every single carbon atom is bonding to either exactly 1 or 2 oxygen atoms. This was the first solid evidence that atoms exist. However, we soon discovered that Dalton's atoms were not fundamentals and indivisible of unit matter that Democritus envisioned. And then J.J. Thomson showed that an atom must consist of smaller particles when he discovered the electron. And his cathode ray experiment, shown right here. The cathode ray experiment. Particles ejected from neutral material were shown to have negative electrical charge since they were attracted to a positively charged metal plate. This means atoms must have within them positively charged or negatively charged particles, but he did not know how they were distributed, so he proposed his plum pudding just a bit later, which is right here. These pluses being positive, being protons, and these negatives being electrons. Until, let's put this away real quick. Until Ernest Rutherford took it a bit further with his gold foil experiment. He fired positively charged alpha particles, which are very tiny, at a thin foil of gold. He was shocked to find almost all of them pass right through the detector on the other side, but around 1 in 8,000 scattered widely with high energy in random directions. He himself said that it was though he fired a shotgun at a piece of tissue paper and the shells bounced back and hit you. This suggested that there is positively charges in the atoms that are highly condensed in the center of the atom, which was given the name nucleus, and that the negatively charged electrons were far away, making the atom 99.95% empty space. That's why alpha particles pass right through, but if they're just perfectly aligned to strike the nucleus, then a huge repulsion between the positive charges makes them fly violently in random directions. So now we arrive at the model looks like this. Let me draw it for you guys. Pencil. 1, 2, 3, 4, 5, 6. Proton, neutron, proton, neutron, proton, neutrons, and around them, electrons. 1, 2, 3. Model that looks like this. Which should be familiar, but we aren't done yet revising our view on atomic structure yet. However, we've shown that atoms exist. Now, let's review determining protons, neutrons, and electrons in atoms, isotopes, and ions. Let's start with atoms first. Okay. To find the number of protons, neutrons, and electrons in an atom, we need to first look at the element's atomic number on the periodic table. The number on the top right here is called the atomic number, which represents and gives us the amount of protons in that element. So we know boron has 5 protons. Also, the number of electrons is equal to the number of protons, meaning it has the same number of atomic number. So electrons, they have 5. Now, to find the amount of neutrons, we need to subtract the atomic number from the mass number of the atom. So we need to round up 10.11, right, this number right here, to the nearest whole number. So if it's 5 and up, you raise it up. So it's going to be 11 minus 5 equals 6. So we have 6 neutrons. Next problem, helium. Atomic number, 2. Protons, 2. Electrons are the same number as the atomic number, so it's going to be 2. 4. If it's 5 and up, raise it up. If it's 4 and down, let it shroud. So 4 minus 2 equals 2 neutrons. Gold. This one's a little hard. It has an atomic number of 79, so 79 protons. Electrons, same thing as protons, 79. Neutrons, we round it up, this 9. If it's 5 and up, raise it up. So 197 minus 79 is apparently 118. I think I'm right. Okay. Now let's find how to find protons, electrons, neutrons, and ions. Okay. Now that we figured out how to find it in atoms, doing in ions, yeah, easy thing. If you didn't know, an ion is an atom with a charge positive or negative, like you see right here. Plus, and everything right here, pretty much. Let me fix that, I made a little mistake. Sorry. The charge results because the number of protons and the number of electrons are not equal. Let's say I have 5. Let's use Zn as an example. Wait, no, let's not use it. My bad. Sorry. Let's say I have 5 positively charged and 3 negatively charges. Then we add these two up, right? And plus 5 minus 3, that's a positive 2 charge. That's an example. Now we understand the concept a little. Let's do an example. We can say that zinc positively has 30 protons because its atomic number is 30 protons right here. Because the atomic number is 30, then the electrons are also going to be 30. Write that down. Okay. Oh, wait, no. We can't say that it's 30. Let me explain why. Silly mistake. 30 protons, right? Plus 2. This means in this Zn, our protons have plus 2 more, which means we have to pretty much subtract 30 plus negative 2, and then we're going to get 28. So this is the amounts of electrons we are going to have. So we're going to have 28 electrons. Our atomic mass is 64, so 64 minus 30 equals 34, so 34 neutrons. We got this one right. Let's move on for the next one, bromine. It shows that bromine has a charge of negative 1. We know our atomic number is 35, but if it has this, that means we don't subtract. We have to add an electron. So instead of having 35 electrons, it's gonna have 36 electrons because of this charge right here, adding one extra electron. And so 80 minus 35 equals 45. So we have 45 neutrons. Hydrogen. Hydrogen has 1 proton. Since there's a charge of 1, then we subtract 1. And it's going to equal 0 electrons, right? So we're going to have 0 electrons and 1 neutron. Next, let's do this. How to find protons and neutrons in isotopes. This might be a little challenging, but I got this. If you didn't know, an isotope has the same amounts of protons but different amounts of neutrons. We can see that carbon-12 has 6 protons, 6 electrons, since the, 6 atomic number, 6 electrons, 12 neutrons. We can see it in the periodic table. Atomic number is the protons, atomic number equals the electrons, and the atomic mass subtracted by the atomic number gives us neutrons. But carbon-14 isn't on the periodic table. It has the same amounts of protons and electrons. All we have to do is find out how many electrons. Carbon-14 is subtracted the mass number and the atomic number, which gives us 14 minus 6 equals 8 neutrons. So we know here that protons 6, neutrons 8, electrons 6. And for this one, protons 6, neutrons 6, electrons 6. Make sense? Yeah. Now let's do these 2 examples. Iron. We see here iron has 26 protons, since the atomic number 26. Same thing, 26 electrons, since atomic number is equal to the electrons. Now for neutrons. Iron 54 has 54 neutrons, so all we have to do is subtract that. 54 minus 26. Let's do the math real quick. 4, 3, wait, no. No, it's 14. Sorry. So it's going to be 8, 2, 28. And for this one, it's going to be 31 minus 26, which is easy math because the answer is 31. Perfect. Wait, no. Is it 31? No, we have to subtract it. Silly me. So, 2, 11, 5. 5 neutrons. Perfect. Next problem. Nitrogen 14, nitrogen 15. 7 protons, 7 electrons, 7 protons, 7 electrons. Subtract. This is going to be 7. This one's going to be 8. Now, let's move on to calculating the atomic mass. Let's see. Sorry. Atomic mass. There we go. Now, is it atomic mass? Yes, atomic mass. The abundance is the likelihood of the element popping up. Now, since we have the data, which is shown up here, we can do the calculations. Calculate the atomic mass by using a simple formula, which I'll give it right here. Average atomic mass equals mass times the percent abundance plus mass percent abundance. Simple. We have 2 right here. So all we have to do is plug it in. So equals 34,969 times this. We have to move this 2 times. So let's move it right now. 1, 2. So we're gonna times 0.7576 plus 36.966. 0, move this twice. 1, 2. 1, 2. 0.2424. Let's use our calculator to put that in. Photo math. So we know, let's do this. Plug it in. 34.969, 0.7576. This equals 26.4925144 plus, let's do the other one, 0.2424. 36.966. This equals plus 8,960,584. Now let's add these two numbers together. 26.4925144 plus 8.9605584, and we're gonna get 35.4530728. This is our answer. Move on to the next problem. We see we have 3 isotopes, but don't worry, we could do the same thing. Average atomic mass. Remember I said you don't have to only do 2, you do an extra one if you have to. So, mass, percent abundance, plus mass, percent plus mass, percent. Okay. Now let's write it down real quick. Equals 23.985 times. Let's move this twice. 1, 2. 0.7870 plus 25.983 times 0.1013 plus 25.983. My bad. Move that 2 times to the left. We don't want any percents. We want decimals. That's what we're looking for right now. Now let's put this on a calculator so we can see what we get. Damn, this is a long problem. It's okay. Glad somebody made calculators. God bless them. 70 plus 25.983 0.1013 25.983. Another one. 83 0.1117. And we get 24.4110574, which is correct. Next problem. Okay. Yeah, I forgot about this. Now let's discuss about calculating percent abundance. Shouldn't be too difficult, right? Hopefully. Let's look at this problem right here. Rubidium has 2 isotopes. RB85 has the mass of 84,9117. Underline that. And RB87 has a mass number of 86, 90, 85. Let's underline that too. If the average atomic mass is 85.467, is that 7? Let me see. Yes. No, it's 8. 8. Amu, what is the percent abundance of each isotope? Okay. We know that rubidium has a mass number of 84.9117, and RB87 has a mass number of 86.9085. But we are looking for is how much percent of all rubidium is in each of these. The trick is that the isotope abundance for particular isotopes obviously has to add up to 100%, or else it would be missing an isotope. So let's make a little chart. Isotope, mass, and percent abundance. RB, 85 and 87. So let's put its masses right here that we underlined right here, 84.917 and 86.9085. There we go. And the percent of, we're going to put X, and we're going to put 1 minus X. 1 meaning 100, but that's a simplified form. So now let's do a linear equation. Linear equation. It says the average mass of 85, we're putting this right here, 85.468 equals 84.9117 times X, which we're going to put this X, plus 86.985 minus 86.9085x, because this distributive property, this goes right here, this and this. So what do we do first? Let's guess. Since the x's are on the same side, let's subtract this side. What you do to one side, you do to the other side. Zero, 85, right? 85. If you plug this into the calculator, let's do it real quick. Damn, that's a big number. 85.4678 minus 86.9085 is equal to this. Negative 1.4407 equals, if we add these two up together, let's see what we get. 84.9085. Did I do that right? Oh crap! No, I didn't do it right. 0.9117 minus 86.90.85. This equals this number. Let's put that in. This number may be scary, but all we got to do is divide it. Divide. What you do the one side, you do the other side. 968. You do 68. Now let's divide this by 1.4407 divided by 1.9968 equals 0. This, but we're just gonna put these two. We just need two numbers, so we're gonna put x equals 72, 0.72. Now we need to find the percent of each, right? So to convert this to percent, we just move it twice, 0. So we know RB85 equals 72%. To find RB87, we just need 100 minus 72%. And this equals 27. Wait, no. I did it wrong. Sorry. Yeah, did I do it wrong? Yeah, I think. RB, this is equal to 7215. You have to move it twice. Move it twice, convert it. So this is going to equal 7215 minus 7215. And we do the math, mental math, and RB 87 is equal to 27.85%. Perfect, we did this problem. Now it's for the next problem. There are two isotopes, chlorine 35, which weighs 34.97 mU, and chlorine 37, which weighs 36.97 mU. Let's underline these. Chlorine. If the relative atomic mass chlorine is 35.45, what is the abundance of each isotope? Let's make a little chart. Iso, top, mass, percent abundance. Chlorine. Chlorine, 3537. The mass, 34.97. And 36.97. And the percent abundance x and 1 minus x. Let's put this in the problem now. 35.45 being at the end, linear equation time. 45 equals 34.97x, because distributed property. Distributed property plus 36.97 minus 36.97. Since the x's are on the same side, let's subtract. And the result, we get negative 1.52 equals, add these two up, and you get negative 2x. Negative 2x, you divide these two, you get 0.76, which equals x. Now let's plug this in. To convert this to percent, 1, 2, 76, 7%. This is gonna equal chlorine 35. Now let's subtract that from 100. This equals 24. So chlorine 37 equals 24%. Perfect. Now time for the last problem. There are two naturally occurring isotopes of lithium. Lithium-6, which has this much mu, and lithium-7, this much mu. What is the percent abundance? They don't give us the total, so if we look at the periodic table, it shows us that lithium, let me write this down. Lithium. Its atomic mass is 6.941. So let's just get right into it and make the chart. Iso, mass, percent, lithium, 6.015, and 7.016. And percent abundance is x and 1 minus x. Let's get started. We know that this is what it equals, so 6.941. My bad if my handwriting looks really bad right now. Sorry. Equals 6.115, because distributive property, don't forget that. Distributive property plus 7.016 minus 0.16. 16x. What did you do the one side, you do to the other side? Let's do that real quick. You do that, you get this, negative 1.001x equals these two. You're going to get negative 0.075. Now we got to divide them. My bad, x. This is x, this is not x. And we divide them. My bad, made a little mistake. Now we have to divide them, 0.075. and 0.075. Let's do that on our calculator. 1.001 divided by 0.075. And we get, my calculator says we get x equals 0. Wait, I made a mistake. Oh my god. Wait, did I do it right? Yeah, no, I did do it right. 0.075, which if we put this as a percentage, we get 1, 2, yeah, we put it 1, 2. So x, the lithium 6, this is gonna equal 7.6%. No, not 6, 5. 7.5%. And lithium 7, let's do that subtraction real quick. 0 minus 7.5. Empty, empty, empty. Take 1, 10, 9, 10, 9, and 10. This is gonna be 5.29%. So lithium 7 equals 92.5%. Now that we're done with that, let's talk about how all of this could be in real world applications. If you didn't know, isotopes could be used in medicine. It's usually particularly radioactive isotopes are used in primarily for diagnosis through imaging techniques like PET scans and SPECT, where they act as tracers to visualize the function of specific organ of the body, and for treatment by delivering radiation directly to cancerous cells to destroy them, allowing for targeted therapy for minimal damage to health conditions. Common examples include common examples can include iodine 131 for thyroid cancer treatment. Also, atomic mass and isotopes are relevant for cancer and nuclear energy. Atomic mass and isotopes are crucial because they allow scientists to identify and differentiate between different forms of an element. Particularly, radioactive isotopes like carbon-14, which is the basis for carbon dating, and other radioactive elements used in nuclear power generation. The specific atomic mass of an isotope is key to understanding its decay rate and its half-life, which can be and is essential for calculating the age of an object and carbon dating or energy released in nuclear reactions. Now, to conclude all of this in one, in atomic theory, we have really expanded, and we've thought of that so much. The thinking we've been to the ground, to all the way to Greek, and now in present 2025, we have our model, and we're not even done finishing it. Imagine 4,000 years from now, it looks totally different, and how chemistry could help the world and benefit in so many ways, helping people with thyroid cancer and carbon dating. We could really discover the world more. And out of this lesson, my favorite subject personally was calculating percent abundance.